Opnemen. Hello, everyone. My name is Gielis, and for the World Bamboo Congress in Taiwan, we present a report on joint research with Nanjing Forestry University and the team of Dr. Pejian Shi. The title of the talk is From Square Bamboos to Superformula, and basically what the goal is we want to develop improved methods quantitatively for forest management, the yields we have and so on. Actually, we report on a novel scientific method for quantifying natural forms for a precise quantitative description of the shapes involved. If we can do that, we can avoid, let's say, qualitative notions to describe leaves or to describe shapes and so on. And actually, this is done in just a few numbers, as I will show, and we call it the simplified Gielis equation. And as I will also show, that originates in bamboo. So actually, my background is from the very first job that I had was bamboo, but mainly in plant biotechnology. We developed with our team a very, very highly efficient micropropagation methods for fast propagation of bamboo, and quantitative and qualitative data and really measurements were key to this. My talk consists of our talk, I would say, or prepared together with the Pejian. It consists of 6 pieces. Background. We'll tell a little bit about the background of Gielis equation, show some examples of natural shapes that we describe, how we measure and scan data, measure and quantify data and process the data, then examples in bamboo and future works. As far as the background is concerned, ever since I started in bamboo, my question was, what makes bamboo so special? They can grow up to 30 meters high, but they don't have really, they bend but do not break, and they all have cylindrical culms, but they're hollow. Question is, do all bamboos have cylindrical culms? And it turned out to be there's a genus, Himala bambusa genus, where a number of species have really square stems naturally occurring. And when I was studying this, I came across a mathematician, Gabriel Lamé, who defined shapes like this. If x squared plus y squared equals r squared, defines a circle, but if you have some number n, you can define any shape in between a circle and a square, and so on and so forth, as you will see in the lower left and the left panel. But you also see that we could use this immediately to describe square bamboos very accurately. Now, what is this formula? So I will show you immediately, but the background is that we could model squares and so on, but not pentagons and triangles and so on that we see occurring everywhere in nature. So in 2003, I published this paper in the American Journal of Botany, a generic geometric transformation that unifies a wide range of natural and abstract shapes, and it caught a lot of attention. I called it originally Superformula, a generalization of supercircles and superellipses, but afterwards people called it Gielis Formula after me. And what is very different from the original x to the n plus y to the n is we transformed it into polar coordinates. And what is important is the factor m. M defines actually the symmetry of the shape. If I fill in m is 4, we have squares. But if I fill in m is 5, 6, 7, I have, let's say, hexagons, heptagons, pentagons, or triangles. And that's very important. And the exponents there, they just give flexibility to the shape, just as before with the Lamé curves. And that proved to be very, very powerful. Actually, we saw also the A and the B written there, and that's basically if A is equal to B, we have a circle. If A is not equal to B, we have an ellipse that can be transformed into a rectangle. But rewriting this by the team, we have some number A in front, which gives an idea about the size, and K is the relation between B and A. And that we have been using this in all of our studies. Now, what do they do? If M is 3, we have triangles. If M is 5 or 6, we have heptapentagons or starfish. And we can use that to model natural shapes, as you can see, not only by deforming circles into, say, shapes of stems or starfish, but also modifying functions. For example, a spiral function could be modified in something that we see also in mollusk shapes. Now, what is very important from a mathematical point of view, this uniform description of natural shapes, very, very wide shapes in just a few numbers, is a mathematical breakthrough, at least in the natural sciences. Now, we have studied with Nanjing Forestry University taking the lead a great many natural shapes. For example, if we use M1, we could do avian eggs, bamboo leaves, fruits of certain plants, seeds of ginkgo biloba for MS3. If we do something triangular, we have use MS3, MS4, MS5, MS6. For example, here are all the avian eggs we could do with MS1 and playing with two numbers. The Chinese white olive fruit. We have the Vinca major in the lower right panel. We have triangular shapes of the fruits of the golden rain tree. We have seeds from ginkgo biloba. And we could test really thousands of specimens, and they all fit very well. And to each number, to each shape, we could assign a set of absolutely very unique numbers. Here are some examples how they fit to shapes of the previous slides are. So very, very good, if I may say. Now, how is this done? You see some shapes here estimated, but for flat objects like leaves, we can directly use a photo scanner to scan them. For a solid of revolution, we have to take into account that it's just a projection that has to be done carefully. And then the boundary planar coordinates are extracted. And there's a MATLAB file, which is available online in so say, ArtCode as well, that extracts the boundary and the shapes. Now, and then the data fitting method just tries to fit the data to the observation, let's say the green ones, to the values that we get in the formula. Yeah. Actually, all this software has been wrapped into a BioGeom package that is available on the internet, so everybody can use it. For ourselves, it has been tested on more than 40,000 specimens. Now, especially in bamboo, you can use it in many, many ways. For example, in describing bamboo leaves, actually all bamboo leaves or leaf blades, if you want to use it in a correct manner, can be described just in 2 or 3 numbers. If we look at cross-sections of plants, on the right you see the square bamboos, of which more than 1,400 sections were tested of Himano bambusa utilis. If you look at cross-sections of spruces and firs, they also can be described, the annual tree rings, so to speak. If looking at a shoot apical meristems, in this case, Pejian and his student by compared thick-walled mosa versus the wild-type mosa, and they could make a very good fit at different developmental stages of the apical meristems. But also cross-sections of bamboo shoots you say, if you look from the sideway, A, B, but if you cut them, you can see C, and then we extracted basically the data, the boundary data, and overlaid them on the shapes. And actually, any of these layers could be efficiently modeled by the formula. So starting at one in the middle down to the outward 25th layer. And this is just in a generality, bamboo combs that can be also, whether you talk about real round combs, which hardly exist. If you look at number 7 and 8, they're not round at all. Number 6 is not round, only 4 and 5 a bit round. And number 2 is basically the square bamboo. But you see that the fit is extremely good. And just using 2 numbers, M is 1, we know that. some number for the size and one or two numbers for the shape. Actually, showing that one of the first experiments was on bamboo leaves, and all bamboo leaves can be put in two numbers, one for size and one for shapes. We tested bambusa, we tested Inocalamus, Oligostachyon, Philostachys, and various of these shapes. And apparently, if you say we take 100 of these leaves, we process them, then you get a plot like this. For example, number 40, or I think number 13, up to number 27, are all Philostachys in gray. But you can really discriminate between all the Philostachys that you have, that you are testing. If you would run the same experiment with an unknown Philostachys, at least in this class that we already tested, you can assign it. So if we go back, if we develop kind of software that has these two numbers in it, we can do all the shapes. In previous method, we used the SGE1, where you only have, let's say, the number A and the number N1, the exponent. But later we thought that the three-parameter model, so A and 2 and N1, could be better. And this was tested a few years ago on various Pleioblastus species. So with larger leaves of quite a different shape, if you know what I mean. This was tested, comparison of goodness of fit between all these models. And it turned out to be that SG2 was slightly better, which could be studied by root mean square error, than SGE1. You had to add one, but still SGE1 was already very good. SGE2 slightly improved the results. These are the results that are published in the paper. There's really differences between the two models that we can, at a statistically sound level, but it's up to choose. SGE2 was better for the shape of all the bamboo species, but was a bit more complex. Now, what we think in future work, at least we have extended this to starfish and all, but at least in the bamboo world, what I would like to do is build a worldwide database of bamboo leaves for very precise identification. So if somebody pulls out of a forest, say, 100 leaves, and we all scan and measured, which is not a difficult process, and compare it to the database, if the bamboo is in there, we will know exactly. We will not need any highly trained botanists, because we know identification of bamboo is extremely difficult, but we will know just, we don't need molecular data either. Will just know from scanning and using machine learning and develop simple apps for precise field identification should allow for everyone to precisely identify bamboos and also quantify yields, quantify the growth in general. Yeah, I just wanted to, last year, my dear friend, Professor Lise, passed away, and it is from him that I learned facts, not fiction, and that's what we need in bamboo. Then in the other things, you will find a number of references. The joint work has led to more than 20 or 30 different scientific papers. And that leaves me to thank you for your attention and enjoy the rest of the conference.